Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 8, 2026, about 3 days ago. It introduces recurrent depth VLA, an architecture that achieves adaptive compute through latent iterative refinement, delivering up to an 80 times inference speedup, while boosting success rates on complex tasks from 0 to over 90%. The paper is titled Recurrent Depth VLA, Implicit Test Time Compute Scaling of Vision Language Action Models via Latent Iterative Reasoning. And as we'll see later, the results for efficient robotic control are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 2 illustrates the recurrent depth VLA architecture, effectively splitting the reasoning process into 3 specialized components. On the left, the pipeline starts by encoding images and text with a standard versus LM backbone to create feature representations. The red prelude module then initializes a latent scratchpad based on these features. In the center, the blue recurrent core iteratively updates this scratchpad, refining the plan over multiple steps without expanding memory. Finally, the yellow coda block translates that refined mental state into concrete robot actions. Figure 1 places this architecture in context. On the left, traditional models like ThinkAct generate explicit reasoning tokens one by one, switching back and forth between internal representations and outputs. In contrast, the center panel shows recurrent depth VLA, keeping the refinement loop entirely within the latent space, avoiding that decoding overhead. The impact is visible on the right. The top graph shows success rates climbing rapidly with recurrence depth, while the bottom chart demonstrates the efficiency gain, with the model running up to 80 times faster than prior baselines. Figure 3 demonstrates this adaptive behavior in practice during a task where the robot must place soup and sauce into a basket. The plot tracks the number of thinking iterations on the vertical axis against the timeline of the episode. Notice how the blue line spikes and dips. For simple navigation at the start, the model commits only about 7 iterations. In contrast, at steps 10 and 25, which correspond to difficult grasping actions, the compute ramps up to 14 iterations, showing that the system effectively thinks longer only when the problem demands it. Table 2 compares fixed iteration counts against adaptive strategies to find the sweet spot for efficiency. In the top section for fixed recurrence, we see that deeper thinking drives better actions. A single iteration yields only 8.4% success, while 4 iterations boost this to 84%. Performance eventually peaks at roughly 93%. The lower sections test adaptive methods like binary adaptation, which stop reasoning dynamically when the model is confident. Notably, these strategies match that top-tier performance, reaching 92%, but use only about 8 iterations on average, effectively saving compute on easier tasks. So, Table 1 places these results in a broader context, comparing recurrent depth VLA against state-of-the-art baselines on the Libero benchmark. The upper sections list standard end-to-end models and token reasoning approaches, which typically rely on large backbones ranging from 2 to 8 billion parameters. In contrast, the latent reasoning section at the bottom reveals that recurrent depth VLA uses just 0.5 billion parameters. Despite this small size, it secures the highest average success rate of 93%. The advantage is starkest in long horizon tasks, where it scores about 85%, significantly outperforming larger competitors that mostly fall below 80%. Figure 7 brings these results into the real world, deploying the model on a bimanual robot arm to perform household chores. The bottom photos display the 4 tasks, which include wiping a dish and toasting bread. In the bar chart above, the blue bars for recurrent depth VLA consistently surpass the pink diffusion and purple pi 0.5 baselines. For example, on the full tile task, the baseline barely functions, yet the recurrent model scores above 90%, proving that latent reasoning adds significant robustness in physical environments. Wrapping up, 2 takeaways stand out. First, recurrent depth VLA proves that effective reasoning doesn't require massive memory or slow token generation. Instead, latent iteration allows a compact half-billion parameter model to outperform 7 billion parameter giants. Second, the 80 times speedup suggests that adaptive test time compute is a viable path for real-time robotics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.